So let's talk a little bit about the process of creating a linear model. The first step is you have to decide that you're going to use a linear model. You should have reasons why you think it might be a good fit. Then you should decide which features you'll actually use of your feature set, decide how you'll avoid overfitting, train the model, and check the model. Now we're going to basically do 1 and 4 in the next few modules, and 2 and 3 we'll see a little bit, but they're going to become more important later in the week and in the course. Some reasons you might use a linear model. You might have clear visual evidence of linear relationships, like in a scatter plot. You might have a value of Pearson's correlation coefficient that's close to -1 or close to 1. Remember, Pearson's correlation coefficient tells you how linear the relationship between two variables is. You might know, because you know something about the problem, that there's a good reason for this to be linear. You might pick a linear regression model because it's simple and easy to understand, and even if it doesn't give you quite as good a fit, it might be worth it for that reason. Or you might pick a linear model because you're just starting the process, and even if you're going to eventually pick a different model, having a linear regression model that you can compare your model to could be helpful. So what's linearity mean? Let's consider the relationship between hours driven on a long interstate road trip and distance traveled. Since miles per hour is roughly constant in highway driving, I would expect the relationship to hold. If I drive 10 times as many hours, I will cover about 10 times as much distance. That's linearity. If you have 10 times as much input, you get 10 times as much output, and it's completely predictable. But consider another example involving a car. This one is due to the great probabilist and scholar Nicholas Nassim Taleb. If you crash your car into a wall 50 times at 2 miles per hour, you will probably be okay. If you crash your car into a wall 1 time at 100 miles per hour, you will not be okay. 50 times as much speed doesn't do 50 times as much damage. 50 times as much speed does much more than 50 times as much damage. This is nonlinearity. So when you're considering your variable relationships in your data set, this is a thought experiment you can do. Now, what about YouTube views and YouTube likes? Will a video with 10 times as many views get 10 times as many likes? I have no idea. If you were wanting to propose a linear model, you would want to kind of think about whether or not you thought this idea was reasonable or have some data to back it up. Another reason that linear models are good is you can always explain how you got your answer in a way that anyone could understand. So like you could say, to predict the price of gasoline, I doubled the price of milk, halved the price of bread, and added them together. There is increasing pressure on machine learning and artificial intelligence from the legal side of things. So you can be held accountable for things that your algorithms, quote unquote, decide. There have been many judgments against banks who are using, or there have been at least a few judgments against banks who are using machine learning algorithms to deny people loans, and they couldn't prove that the algorithms weren't discriminatory. Basically, to defend your model, you have to understand how it works, and if there's any real money on the line, you may have to be prepared to testify about how it works. For instance, there's a company that does background checks on prospective renters, and it has had several glaring instances of times where it misidentified the person it was doing the background check on, and all of these are turned into lawsuits, and all of these lawsuits got settled for undisclosed amounts except for one that is still pending. About 43 million people get new apartments each year. So even if you just have a 1% error, that's 430,000 people who are incorrectly impacted, and that's pretty serious. One thing you can do to improve your linear models is to decide which features you can use. So there are two things you can do. One is you can get rid of features that aren't going to work. They're missing too much of the data. They don't seem to have a strong relationship with the target. It would be illegal to use them, like you can't use gender data in hiring, for instance. You could also add new features, which are usually transformations or combinations of the existing features, to account for nonlinear relationships. So paring down your features, getting rid of some of them, is called feature selection. Creating new features is called feature engineering. And we'll talk about more of those, both of those, a bit more later. So that's a quick overview of some aspects of the linear model process. In the models that you're going to see right now, we'll be using all of the features, and we're basically just going to do a quick check that linearity is reasonable. But the reasons that linear models are good go beyond just how the data looks, and they cover some other things like explainability, simplicity, and yeah, let's get started actually building some linear models step by step.